Thank you very much for the introduction. First of all, I would like to thank Radu and his team, and also the group of people worked around this idea of one word seminar during the pandemic. It was fantastic, to be honest. We were hopeless a little bit to how to contact people, even how to provide the videos to our all the students. It was really hard, but this was really helping us. Thank you very much, Radu, and all the team. So, and thank you for invitation. Today, I would like to talk about a Moreau envelope. Everybody here, I assume, that knows about Moreau envelope, and there are many experts here, but we want to have a little bit of a fresh look at the Moreau envelope to see if we consider some kind of higher order Moreau envelope, which type of property we can get, or if we can use the properties of this Moreau envelope, can we construct some type of, how to say, two-level optimization framework that we can handle a little bit more complicated problem in non-smooth non-convex optimization. Okay, so I am starting with the problem that we are dealing with. So I have a function phi, which is a proper and lower semi-continuous, and I assume that this minimization has at least one solution. There are many field of application, machine learning, statistics, signal processing. There are many of them that this function phi is not necessarily convex. So you may ask me, okay, in all of these fields, usually we have a composition of a function. Okay, I don't consider any structure for this function at the moment, and I try to deal with a little bit structural problem later, but overall, for solving such a problems with high order, what do I mean by high order? I mean which level of information from function phi we expect. If I am dealing with a zero order oracle, then derivative free. If I am dealing with first order, second order, or high order optimization. So there are several developments, and most of this development is based on two approximation of the original function phi. So which type of approximation we are expected? As a mathematician, the first things that comes to the mind is a Taylor expansion that we can see here, and many of our colleagues did a regularized version of this one and tried to develop some optimization based on this. And the second type is based on the proximal point method, but this time with a high order regularization. We know that the case of Martinez, and after that with Rockefeller, was the power here P is equal to 1. So basically the power 2 we have for the regularization term. But here we want to deal with some things with the power P. And I will give you some motivation why this power P could be useful during the talk. And so what we do usually, we assume this subproblem, and we find this point, and based on some process, we accept or change this point. So this is the process. Let's go first have a look at a convex setting. What happens in a convex setting during the last few years? What happens, which type of a problem we have dealt with? Okay, so this is very interesting to see. Started from 2018 with the good work of Nesterov. He started to say that if we want to deal with this type of minimization, especially if it is in a composite case, you need to have a convex subproblem. Okay, so to make a convex subproblem, let's make one more comment here. This Taylor expansion, even if we have our original function is convex, we cannot show it is convex. So it could be non-convex. So this is one of the main difficulty. So if I have an optimization which is a convex, why should I have a non-convex problem? So it would be problematic. To be honest, why do we do that? This is a problem. What Yuri did, it is interesting. He said that if we add enough, we make this parameter Lk big enough, then I can show that this Taylor expansion will be convex. And so this revolutionized everything that, okay, my subproblem is convex, therefore for solving a subproblem, I have something nice. But it adds on some difficulty as well. So what is the difficulty in a first glance to this? How I can solve this problem? This is a big difficulty because it doesn't have a Lipschitz gradient. And so even in a case I don't have any regularization, I come with a trouble. So we will talk about this aspect later on, but let's have a look at the complexity for the convex case. Okay, if we apply the proximal point method, a fresh plain proximal point method, we get epsilon to the power 1 over p, accelerated version, 1 over p plus 1. And if we use the extra segment search inside, we get some better complexity, which would be 2 over 3p plus 1. If we have a look at, for the convex case, have a look at the optimal version, we see that this one is the optimal one. So it means that if I can solve the subproblem efficiently that has no complexity for me, I am optimal. But there is a big but here. Can I solve this problem efficiently such that it has a no cost? No cost is impossible for us. It's impossible to say I have a no cost here. So we studied this fact in this published paper already, and we could only show that if p is equal to 3, I can get something amenable, which means that I get a logarithmic factor of 1 over epsilon. So I say it is negligible in a complexity if I get such a things. It means that the algorithm I need to solve the lower level set need to be linearly convergent, but not local linear, should be globally linearly convergent. So this is a big problem. How many algorithms we know that it is globally linear convergence if I am in a non-convex setting? Even in a convex setting, I don't have a strong convexity. I come with the issues, to be honest. So still, this is a problem, even in a convex case. But if we have a look at the structure of this, both of these two subproblems, and we can get something like epsilon to the power 1 minus p. Unfortunately, this is include p, so it is still pessimistic. And the whole complexity, if p is not equal to 3, all the costs come from here. Maybe this is the subproblem. The cost of solving a subproblem is even more than the outer loop algorithm that I have. So this is one of the issues. Let's have a look at some non-convex setting. I will take a look at some of the good papers around this area. So we have either a smooth one or some structured non-smooth one. So still we have a look at this algorithm with regularization, adaptive regularization. Cora is here. I'm really happy that she's here. Okay. This type of development, unfortunately, we have a complexity for that, but we have a complexity for the outer loop only. So the whole complexity of the algorithm, even in a convex case, while this is very interesting, this is very beautiful, is given in all these nice papers, is only about the outer loop. Outer loop could have a nice complexity, but what happens about the inner loop? This is still a problem. Okay, and we see that still the structure we can deal with a non-smooth one in a high order. We have a regularization which has a very simple structure. It is a separable one and it has a very simple structure. Now, the question is, can we deal with something with a little bit more elaborated non-smooth part? This brings us to some adaptation of idea of a two-level optimization by the smoothing using the high-order Moreau envelope. Some things like the framework we have here, and we try to assume that f is smooth enough and G is prox-regular. It means it is wide enough. It is not like only separable in a convex case we consider. We want something a little bit more. So prox-regular is amenable, especially if we consider the second order development. Boris is here, and so he can certify that it is for second order versions. If we want to develop a second order method, that's really important. So this is at least the class that we want to deal with. Okay, so what can we do? We consider a two-level method. If we do the smoothing on this function based on some methodology, it could be a Moreau envelope, forward-backward envelope, Douglas-Rochford envelope. Fortunately, in this conference, there were a wide range of people talked about this topic. And so it is very important to see any of them I can consider here, but the case is the information I want to use is high order. Okay, if I want to deal with a high order, then I need to consider high order regularization. Therefore, I need to consider some Moreau envelope or also forward-backward envelope with a high order regularization. So this is the main idea come from here. So in this stage, I will talk about some basic information, basic results we got about a high order Moreau envelope that I can construct some gradient-based method for this two-level methodology. There are many more results here, but I cannot just talk about that because I don't have enough time. So what I mean with this nice construction, proximal point method with the power P. Fortunately, Patrick is here in the book with Heinz and Patrick. They studied some properties of this type of function for lower semi-continuous functions. Some basic properties still exist about that, but nothing about the differentiability that I am interested in. Something's not about the prox-boundedness. Some nice construction is still hidden here about this. And I construct a Moreau envelope with power P. This power, for the first time, could be bigger than 1. Is strictly bigger than 1, so Hausdorff is not considered here. So anything's bigger than 1, so including the classical setting power 2 as well. Okay, so in order to make sure that this prox that I defined here, before here I made this abbreviation here. By hope, I mean a high order proximal operator, and by home, I mean high order Moreau envelope. And hope for a home is an important factor in recent years because of many wars we can see. So hope for home for everybody around the world. Okay, so this is one of the messages from Radu in optimization, one-word optimization. Okay, now let's have a look at the properties here. If we assume that my function phi is a high-order prox-boundedness, it means that the high-order Moreau envelope is bigger than -infinity, then I can show that the prox operator is non-empty and compact, and my high-order Moreau envelope is continuous, and it is less than function, the original function phi. Okay, so this was the first one. Now I want to have a look at the differentiability of this function. And as I told you, I need at least to make sure this is working for the class of a prox-regular. For sure, for the class of generalized convexity, several classes of them, like pseudo-convex and several other classes, we have a different result. We already proved that. We have it as a separate paper than what I am presenting here. But here, I'm trying to focus only on prox-regular case. If you know the prox-regularity, because there were a few colleagues talk about it, and many functions that satisfying this, therefore it is a wide area and wide area class of functions. If my function, first of all, I need to make sure for the differentiability, I need to divide my high order one in the two cases. When P is between 1 and 2, and the case it is strictly bigger than 2, because I need the different techniques to show the differentiability. Okay, in a case that I have in a case P between 1 and 2, I can show that a proximal, yes? No.
You can say
exactly. Okay, so let's have another look here. I can show that the proximal point method, if I consider this prox operator, if I consider the constant are big enough, always the prox operator belongs to this area, and it is single valued, and my function is continuous. Okay, this is the first result that we have. But in order to show the case that I have a P bigger than 2, I need to make a restriction. Unfortunately, for the class of prox-regular one, I cannot do that. So we define Q prox-regular, which means that the definition is the same as what we have. But here I have a power Q when Q is strictly bigger than 2. Okay, in this case, if I have this property and gamma is restricted to this interval, then I can show that my function is C1, prox is single valued on some special area. And this special area is very important because I will tell you, if I want to make my gradient type algorithm works with a constant step size, I need some Lipschitz gradient or Hölder gradient at least to deal with that. Okay, so by now only I know I have a differentiability, but do I get a weak smoothness for this gradient? So this is something we will study now. Okay, before doing that, let's have a look at why sometimes we use P. There are several reasons, but here we give you only one. Let's consider this toy example, x3 plus 1, absolute value of this one. This is this beautiful curve here, and if you have here gamma equal to 1 and P equal to 2, you see that we have some approximation, but here we see that we are non-smooth. Therefore, it means that if I want to make this function smooth, I need to use a smaller gamma. A smaller gamma, we know in optimization means my gradient type methodology is slower. Therefore, I need from 1, make it a 0.1 to make sure this is a smooth approximation. But let's see what we do if we consider P equal to 3 in our construction. We see that with 0.2, it is working. So, and this is a big difference because it makes my algorithm much faster if I have a better gamma, better step size. Okay, so now it's a time to talk about weak smoothness of my function. What do I get? In both cases, when we studied this, first P belongs to the 0 and 2. In this case, I can show the prox is Hölder gradient with power 1/2, and the gradient is a Hölder with the power P minus 1/2. And in a case that P bigger than 2, there is this parameter LP and kappa P such that the prox has a Hölderian exponent 1/P minus 1, and the gradient has a 1/P. This is important because you see the difference from here to there. And why I consider that the prox, how to say, the prox exists in some area, in some neighborhood. Why it exists in U? Because if I don't have that, I cannot show these two theorems. This is really important because in a construction, I want to deal with huge scale optimization. Therefore, I need a constant step size. This is some things I want. Okay, so this is a construction I did. Now I have a tools. To be honest, there are much more properties here to talk about, but I skipped them to talk about the gradient method. For sure, everybody know about weak convexity here. The definition is G plus sigma over 2, norm to the power 2 is a weakly convex, and this is a generalization of the class of a prox-regular if it is a global. Basically, the globally prox-regular, Heinz in one of his papers showed that then it is a weakly convex. Okay, so, and there is a characterization here. I wouldn't talk about that because several people did already. Now, let's have a look at the assumption I need to make some algorithmic. Okay, the first thing you will ask me, okay, you have a power P. Do you have any solver or do you have any calculus to make sure that a prox exists at all? But to be honest, I could only construct toy examples. But in a practical example, I wasn't able to show that a prox is computable in a closed form. I couldn't do that. So what we do, we consider some approximation of that, and we show that in the class of weakly convex one, it may be a single value, therefore it could be a convex problem, and we can always approximate that. Okay, so we assume there is these errors, the sum of which is summable here as we assumed here, and the prox recently. Boris and some of his colleagues also considered some structure very close to this one, a little bit different, but very close to this one, but with a p to the power 2. Now we assume I have some oracle, and in this oracle, prox, approximated prox, is close enough to the original prox, and I have this upper bound for the epsilon k. And even not that, function values satisfy this beautiful inequality that if we consider some, yes, up to 5 minutes. Okay, I will be fast. Okay, so if I have this structure, then I can construct some approximated function, which is based on approximation I got from prox. The gradient of the Moreau envelope have this structure. So you may ask me, okay, why you didn't use forward-backward envelope? One of the points which is important here, I don't see any matrix multiplication here. When you use the forward-backward envelope, you have a matrix I minus, for the first smooth function, I need a Hessian of that function. But here, I don't need any structure. Therefore, any type of structure I have in function phi, as long as I compute the prox, is valid for me. That's why I can do generalization. And for some difficult example that I show one of them at least here, I can apply my algorithm here. Okay, then I construct the approximated gradient by replacing the approximated prox in this formula, which is given here. Okay, I did that. I construct this algorithm. My first algorithm is very simple. It is a constant step size, but you see here I have some exponents, extra exponents, which is power is positive. Because of that, we can consider the name dynamic step length. Dynamic step length I couldn't put here because it would be too long here, unfortunately. So I only put a dynamic here. I have this structure, and if alpha k belongs to this area, I can show the convergence of this method. But the case is, here I need some kappa p, and this kappa p constant, I can construct it. It is fully constructible, but it could be too big. Since it is too big, therefore, this would be too small, and my algorithm would be ruined. I will show you in an implementation. This is not a good idea to deal with this, because I need that kappa to make sure that Hölderian constant exists. Then I am adopting this with some line search, And I try to use this line search. You see, the only difference is this repeat until that I add here. I construct this line search, and I use this line search to approximate some parameter Lk of the Lipschitz constant, the Hölder constant, sorry. Okay, if I do that, I get this nice result that the gradient of the approximated function and the envelope goes to 0, and I have this complexity for the norm of a gradient. Okay, then if I consider the Kurdyka-Łojasiewicz one, fortunately Lee and Pong are here, both of them. If I assume the function phi itself has some exponent for the Kurdyka-Łojasiewicz, and p is between p minus 1 over p and 1, I can show that my envelope function has the same exponent, which is very important, and it is a beautiful work that we followed their line of research. Okay, so if I have that, I want to see if there is any possibility to get a linear convergence. But unfortunately, I cannot prove the linear convergence with this restriction, because this is too big compared to what I have here. Here you see I have a p minus 1, exponent should be p minus 1 over p plus 1, but here in the here I have p minus 1 over p. So I cannot assume that my original function has this exponent and I get a linear convergence for the gradient method. Therefore, I assumed here, as Tinky suggested to me, assume that my exponent is this one, and I can show the linear convergence for the function value and our linear convergence for the norm of points and also the gradients. Okay, I'm finishing. So I just want to mention here robust low-rank matrix recovery. You see this beautiful problem we have here, and we want to minimize this one. You see, I don't have any smoothness, I don't have any structure. One of the author, Antoni, is not here, unfortunately. He was a person who developed this model. So I can apply my methodology in this one, while I couldn't do use a forward-backward here, because there is no smoothness here. Okay, now I consider three strategy for the parameter L. When I start each time from L0, I use the LK of the former one, or I use this type of approximation, and this is what approximation of the usual LK we have. So we have a forest strategy. Let's have a look at some numeric. This is the original bound that I get. And you see the line search works much better than that one, and we stopped the algorithm in 30 seconds. So if I compare the four scenario, sorry, that one I made a mistake. This is a difference between p. If I consider the different p, this is a p power 2. You see, this is performance of p to the power 2. If I decrease the p to the 1.25, then I get a much better result. This is one of the reasons we consider this power p. So if I compare the four scenarios, we see that S1 that I start each time with some L0. L0 is some small approximation. I can have this one. Okay, so in total, we had some smoothing by level optimization. Maybe people doesn't like the word by level here because we have only two levels of optimization here. We consider upper level and a lower level. So we can use accelerated gradient method, second order method, higher or possibly higher order method based on this envelope. And inside, how to solve a subproblem still is some things we need to deal with. No Euclidean proximal gradient method, because this function doesn't have a Lipschitz gradient. And also I applied one of a nice idea of Jura here for the subproblem, because we don't have a Lipschitz gradient here, and it's almost work well, sometimes not, for me at least here, but very interesting. And Bella, which is superlinear convergence to none, which is basically Brakeman envelope. We use those smoothing to deal with the subproblem. Okay, all the work was based on a joint work with my PhD student, Ali Raza Kapkani, for high order Moreau envelope and beyond convexity, which we try to make this bi-level smoothing methodology, and a few works with Yuri. This one is published, and two more of them are in a review at the moment. Okay, thank you very much. This was what I wanted.